Okay, I think this is working. Uh, Hi, I'm Piper. I'm in Toronto. Uh, I'm going to be talking about joint shapes of quartic fields and their cubic resolvents. I want to thank the organizers for inviting me and for letting me record this ahead of time because I don't have childcare. So I'm a single parent, and there's really nothing I can do about it if my kids need something. So instead, I'm just recording this at 3 a.m. like a normal person. Okay, so this work is joint with Christelle Vincent. Okay, awesome. So why am I here? uh, I don't know. I really struggle with what we are doing, and the fact that I'm recording this at 3 a.m. in my ridiculously messy apartment is not helping me understand why I'm doing this. So I guess I just want to say that everything sucks, not just for me, for a lot of us. And I don't think we talk about that enough. But I still do math. So I wanted to give this talk because yeah, it's math and it's fun. I forgot to start my timer, so uh, I get to still maybe run out of time, even though I'm recording this ahead of time. Awesome. Okay. So things that I've dealt with. So I started thinking about joint shapes while in the before times, and I was really excited about it. Um, and then a lot of things have happened, so I just thought I'd write out some of the reasons why I've struggled to do math over the past year or so. Okay, so I mean, this isn't part of my talk, but it's on my mind always. All of these things are always things that I'm dealing with, always. And so, why does it matter? At some point, I was given the advice that every talk is a job talk. Um, is this a job talk? I don't know. It's like I don't care anymore. I want to, but like, productivity, right? We're all measured on our productivity. And some people have like really, really just done a lot with this pandemic. And that's like great for them, but I don't think I deserve any less because of all that I had to deal with. Um, I think we should be allowed to have mental health issues that we have to deal with that like get in the way. Um, and I'm just kind of like, I guess I'm just upset. One of the things that the pandemic showed me was how little community I have in math. I mean, I'm on Twitter. I'm part of Math Twitter, and I do find community there. But like when the pandemic hit and I was in Hawaii, uh, it just felt like the university didn't care about me, about the students. You get these emails, self-care, and, you're doing great or whatever. I don't even remember. I've blocked that out. But I just felt like, shouldn't we care about each other? Shouldn't we be trying to get through this together? And I'm told that the workplace is not where you should look for a community. Um, and okay, that sucks, but like whatever, I guess that makes sense. And like you grow up, you live in a place, you have a community, you get a job, like that's just where you exchanged labor for money. Um, and so whatever, but in academia, we have to keep leaving over and over again. So if you're telling a grad student, this is not the place where you should have community, or a postdoc, well, I just got here, you know? Um, so during the pandemic, I had to move to Toronto, to Canada. Um, I wasn't allowed to not do that, even though I didn't teach in the fall, because in order to get a paycheck, I had to get a work permit. And in order to get a work permit, I had to cross the border alone with two kids. And it was just awful. And I don't have community here, and maybe that doesn't affect you, but it affects me. So I don't know. I want to do math, but it's super hard. Okay, right, but math, it's going to be math talk. I submitted a whole abstract, right? So I'm here for fun, and here's some bunnies to represent math Twitter. Okay, so what do? I study shapes of number fields, but I count them. So I want to study the shapes of number fields because that's where my heart is. But I don't know if I can say that there's money in anything that I do, but asymptotics is where that's the capital of arithmetic statistics, is actually using shape to count number fields or whatever. I don't care about the count, but I do really enjoy shapes of number fields. So we're gonna talk about both, I guess, whatever. Warning, no predators allowed. Now I don't have a copyright, I can't hold my theorems to myself. I'm in this for everyone, but if I had any control, I would say that if you are out there harassing women or thinking that Me Too was way out of control and really messed up your day, just please don't use my math. Don't learn my math. Don't use my math. Don't speak my name. If I had any wish, that's what it would be. Okay, so number fields. I study number fields. I think this is to get. I'm not going to define number fields, I guess. I don't know. Finite extension of Q. But here is a doodle of mine that I thought would be soothing in these trying times. So here are some fields. Okay, so I'm going to talk about quartic fields. I guess that's what the work is going to be. But for ease, let's begin with a degree 3. So we start with K, cubic number field. Okay, but K is fake news. So this is a perspective I'm trying to gain and get more comfortable with. The idea that when we talk about a cubic number field, as far as Q is concerned, these cubic extensions that come from the same irreducible cubic polynomial, they're indistinguishable. Okay, so instead of thinking oh, what would the shape of K be? You really have these 3 number fields that all together, your structure should come from all 3 of them. Okay, so sweeping things under rugs or whatever, just try to get flavor so you know who I am and what I do, and maybe everything I say is not true. I don't care. Okay, it's I don't care. So anyway, we have Minkowski embeddings, I think they're called. So given your number field, you have a ring of integers, okay? And since I told you that my cubic number field, it's really this triple of number fields, the conjugates, I guess. So you can take your okay, your ring of integers, and you can send it to triples in this case, where you have the 3 different embeddings of K into C, I guess, of OK into C. And so you will actually get a full rank lattice. Now, to be nice to my brain, I think about just your standard embeddings, just into C, just what, looking at the roots of the polynomial. But in fact, you'll get a subspace of C3, and really it's R3. And so, you can the J sub R is going to be every time you have a complex embedding, you actually take the real and imaginary parts. But I just don't want to like explain why that's the same. So whatever, just like go with me, and yeah, just come with me on this journey. Okay, so anywho, after further mathing is done, then from your OK, from your ring of integers, suppose you could write it as like z and then alpha 1 z and alpha 2 z, then we are going to project onto like the orthogonal complement of 1 or of j r of 1, whatever. I don't care. I just want you to know that we're getting rid of that z. Okay, that's the only thing I want you to like think about is we're getting rid of that z. And we're not just like chopping it off, we're projecting. If you want to like visualize it, but I don't want to visualize it. So like, it doesn't matter. The point is that if we want to look at all number fields and talk about like, are they random? Like, is there a structure random, or is it like, I don't know, determined in some way? Well, if I know that one of my like I have the basis vector 1 or JR of 1 like all the time, then like, oh, it's not random. Okay, but that's like absurd. Okay, so we're just gonna get rid of it in this nice way. I'm oh my goodness, what did I do? I'm telling you that it's nice. Gosh. Okay. That wasn't supposed to happen when I record ahead of time. Such is life. Okay, so anyway, point is that, so now you have these two basis elements, JR of your alpha 1 perp and JR of alpha 2 perp. And so we're actually going from a cubic number field, we are going to get a rank 2 lattice. So a lattice, okay, if you have two vectors in R2, two arrows alike in dignity, then you take the z-span of them, right? They tile the plane with parallelograms, okay? Parallelograms have shape, yeah, see? It's all coming together. Okay, so we turned our OK into the z-span of these two-dimensional vectors, yeah? Okay, awesome. Okay, so in general, if you have, so forget about number fields for just a second. In general, if you have a lattice in our n-1 for some reason, the space of shapes for that is going to be this mess. So it's not so bad. So if you take your n-1 vectors in R to the n-1, they determine a parallel thingy. Okay, so that makes, you put those vectors, your basis vectors as rows, and that gives you an element of GL n-1 of R. Okay, and then on the left, we have, we're modding out by change of basis. Okay, so GL n-1Z on the left is just gonna send like your rows to linear combinations of your rows. So it's doing nothing to the lattice, literally exact same set of dots. Okay. And then on the right, we have scaling and rotations and reflections. That's what we're modding out by. Okay, so a lattice, the shape of a lattice is the equivalence class of all lattices with that shape. Okay, it's just the set of all lattices that differ from any given one just by scaling, rotating, reflection. And then since we're looking at matrices, not lattices, we also have like all matrices in all bases that are the same. Okay. And so because of that projection thingy, our degree n number field, you always drop a degree, a dimension when you're looking at the space of shapes. Okay, so our cubic fields they're associated with some two-dimensional lattice. And so this is the space of shapes for two-dimensional lattices. And it's really nice. So you can always just make it so that one of your vectors is from 0 to 1, on the positive x-axis. Okay, and then where the other one ends up tells you what type of shape you have. Okay, you can have square. Okay, why these two both are rhombus, yeah, you can see that is takes a bit more thought. Okay, rectangular, okay, blah, blah, blah. So this is nice, but let's move on. Fun fact, okay, so this was in my thesis. And I just said n equals 4. So the shapes of S4 quartic fields, S4, just think of that as like random, okay, are equidistributed in the space of shapes of rank 3 lattices when ordered by absolute discriminant. Okay, so I just think random. Okay, so your space of shapes, when you have rank 3 lattices, I can't draw this nice picture. Sorry, but it's some picture. And the point is that the space of shapes of lattices, these are, every point there is some kind of lattice, but not every point goes to a number field. So the question is, where are the number fields? Okay, and the answer is they're everywhere. Okay, and so how we did this, so this is kind of a mess, but it's got colors, so I feel like it's okay. So what we want is to count these number fields. Okay, we wanted to count quartic number fields. Oh, I forgot to write shape over here. We can see the shape. Oh, I did write shape. We can see discriminant. I'm still nervous, even though I'm just all by myself. Okay, we want to count number fields. Okay, but they're like they're like the Legos on my floor. They're everywhere, very hard to deal with. Down here at these hearts, we have something friendly. So VZ is just integer points. It's like Z12, it's just integer points in a vector space. And this GZ is just very nice group action. Okay, so VZ mod GZ, this is like very friendly. Here we have geometry of numbers, we can count points. Okay, so that makes us happy. What we wanted were these Ks, okay? So like, if you can count your OKs, that's the same as counting your Ks. So then what we have is we have these pairs of rings. Okay, so Manjul Bhargava has these parameterizations between this nice happy place and pairs of rings where R is a quartic ring and S is something called a cubic resolvent, which I didn't have to deal with because when R is maximal, when it's actually equal to OK, then you have a unique resolvent ring. So you can just like not care about it at all. So what we did was we counted things in the happy place, and then you sieve, okay, because maximality turns out to be a P thing. Very nice, because we're in number theory. Okay, so you sieve, and then you get your answer, blah, blah, blah. Okay, awesome. Okay, but then it's like, what about these, what's going on here with these resolvent rings? So just to say some things that are hopefully true, again, I started this in the before times. Okay, so you've got K over Q. Okay, K is a quartic number field, so degree 4 over Q. It's S4, which means it's got no intermediary fields. You add one root to your quartic and like you got nothing else. Okay, you have to get all the way to S4, all the way, you have to add all of the roots to get up to your Galois closure. Okay, so in K you have OK, and in OK you have other rings that are not maximal. So the parameterization use the multiplication table of R, and you get out this other ring, S. And I am not going to be doing that. But you have these pairs RS. And so the idea is that you have this other field F. Okay, it's the cubic resolvent field. So you have, for every time you have this K, you have this F. And so the parameterizations in my thesis, or that Manjul made that I used in my thesis, are these RS. And we have that the discriminant of K is the discriminant of OK. I assume by definition, I'll forget. The discriminative of F is equal to the discriminative of OF. Okay, and the discriminative of R is equal to the discriminant of S. So that was where this resolvent pair comes from. Okay. So to count the quartic rings, we sieved to get the maximal OKs, and they have a unique SOK, but these SOKs are not necessarily maximal. Okay. So anyways, this is just kind of like some background information, I guess. So the question was, since we had these pairs of RS and they sieved to these pairs OK, SOK, where we didn't care about the resolvent, what happens though if we hold on to these resolvents and try to look at the fields K and F? Okay, so are the shapes of K and F equidistributed in the space of cubic and quadratic lattices? Can I say quadratic lattices? Rank 3 and rank 2 lattices. Okay, so that's a question. Some things. Okay, so the shape of K, so I didn't feel like adding the notation for joint shape, but okay, so if you have the pair shape of K, shape of F, that's the same as the shape of OK, shape of OF, right? So the parameterization, this VK is going to be an element of VZ. I have not defined any of this because this is a flavor talk. Yeah, flavor. Okay. So we have some like tuple of integers, which corresponds to this maximal OK and its unique resolvent ring SOK. But like I said, SOK is not necessarily maximal. So even if I like know I called it the 3-2 shape. I just made that up like an hour ago. Even if we know that shape for VK, which is just some integers, right? That's not necessarily the shapes that we want, because that's the shape that would give us the shape of the ring and the shape of the resolvent ring. But the resolvent ring is not necessarily the shape of F. That's the obstacle. So without that obstacle, we already know that the joint shapes of like the rings are equidistributed, pretty sure, in the before times. But now we have to deal with this small obstacle that we've been dealing with throughout the pandemic. I mean, no, we haven't been doing anything in the pandemic because we are human beings in the pandemic. Anyway, to the index. So we have our K, quartic field, F, cubic resolvent. So we have OK and its unique resolvent ring SOK. SOK is in some maximal ring OF, ring of integers of F, but they're not necessarily equal, which means they have some index, which we've been calling M. Okay, by math, there exists a nice basis. So I've been writing nice, but then on the slide, it didn't look so nice. So I chose heart as my decoration. So there exists a nice basis, beta 1 heart and beta 2 heart, such that SOK, so there are, oh my goodness, I did it again. So there are a basis of SOK. When you divide beta 2 heart by M, you get a basis of OF. Okay, so this is the theory of elementary divisors. So if M is square free, this is like your only, like you do get this, and then there's like another case, but this is a talk, so who cares? Okay, so then my plan was to use a hammer matrix which sends VK heart to something else. So the idea is, if you just look, right? If you just look at the, oh my goodness, I'm so sorry. So if you just look over here at your SOK and OF, so I can take a matrix that just divides my basis by M, like that doesn't seem too hard. But when I'm acting on my forms, I have a basis of okay and a basis of S okay. And so dividing by M on the cubic side, it does something. On the quartic side, that like it's not a quartic ring anymore. But you know, it's there. And the point is that whatever's going on, the shape, when I take the 3-2 shape of this like new thing, hammer of VK heart, I get the shapes that I want. So with this hammer matrix, which I hope lives on, with this hammer matrix, we're able to isolate the shapes that we want. And then in the before times, I worked it all out and my error was too big. And so Christelle has a fix that we haven't been able to talk about because the world has been on fire. So I look forward to working it all out. And if you want more, then you should catch us on Twitter at The Shape Show, which we do sometimes. Okay, so thank you. And I'm in the audience to answer questions unless we ran out of time because I didn't start my timer right away. Okay, awesome.